Just as we saw properties of functions, namely 1, 1, and onto, we will see properties of equivalence relation, namely reflexive, symmetric, and transitive. These might seem a little non-intuitive, but that's kind of because you're seeing relations for the first time, whereas functions you have seen for a long time in your life. And this is just an introduction to relations. So it's okay if you don't see why these things are important just yet. But if you do some advanced course in algebra or in like some abstract computer science course, you will see why these are extremely useful. But for now, we'll just do some superficial definitions and talk about how these are related to partition. We'll see 3 properties of relations. So let me set up some notation. Let A be a set, and let R be a relation on A, which means that it is a subset of A cross A. R is called reflexive if for every x in A, x is related to x. So something is related to itself. Then symmetric is more natural, I think. R is called symmetric if for every x and y in A, if x is related to y, then y is related to x. Remember that if then statements are true when the if is false. So if x is not related to y, then I'm saying nothing. But if x is related to y, then y is also related to x. So in that way, the relation is symmetric. And finally, transitive. R is called transitive if for every x, y, z in A, so for every 3 elements in A, if x is related to y and y is related to z, then x is related to z. Okay, so this is saying, yeah, that's all. So if I wanted to draw it using picture, the first statement, reflexive, is saying that if I take an x, then for every x in A, I have a loop like this. So this is reflexive. Symmetric is saying that if I have 2 elements x and y, and there is an arrow like this, which encodes x related to y, then there is also an arrow going backward that encodes y related to x. That's symmetric. And transitive is saying that if I have 3 elements x, y, and z, and I have an arrow that encodes x related to y, and I have an arrow y to z, then I also have an arrow from x to z. Okay, so that's transitive. It's hard to motivate these, so you just have to remember them for now. Finally, just like when you have a function and it's 1 to 1 and onto, you have a new name for it. It's called a bijection. Similarly here, we have a new name called an equivalence relation. And an equivalence relation is a binary relation that is all 3 of the above. So it is transitive, sorry, it is reflexive and symmetric and transitive. And equivalence relations usually have a nicer symbol if R is an equivalence relation. So far, we just done some definitions. Now let's do some examples. And I'll repeat the examples from the previous video. So if we have A is the set of all the students in the class, and I can have the relation, I'll denote it like this: A or B if A and B have the same age. And similarly, I can have B is set of everybody who has Facebook accounts. And I can say A or B if A, B are friends. Now let's see if these two different relations are equivalent or not. So I have to check three things: reflexive, symmetric, and transitive. For reflexive, I have to ask for every student, is it true that they have the same age as themselves? And yes, you have the same age as you. That's tautological. And so this is true. Let's look at the Facebook example. Is it true that you are friends with yourself on Facebook? I don't know if this is technically true or not, but let's just call this true, I think. Symmetric. If A and B have the same age, do B and A have the same age? Yeah, again, tautological. And so this is true. Now let's look at the Facebook. If A is friends with B, is B is friends with A? Yes. So that is also true. Now transitive. If A and B have the same age and B and C have the same age, do A and C have the same age? Yes, because they have the same age, and so the final has the same age. This is also true. What about Facebook? Is A is friends with B and B is friends with C? Is it true that A is friends with C? This is false. It doesn't have to be the case. And so here we see a false. And so we see that having the same age is in fact an equivalence relation. But being Facebook friends is not an equivalence relation. Now, equivalence relation is an amazingly important concept, because having an equivalence relation lets you partition your set. What do I mean by that? So I can take the set of all students, and because I have an equivalence relation by using the same age, I can partition the set of students using age. So I can say the partition 1 contains students who are born in, let's say, 1990. Then the next one is 1991, 92, 93, and so on. And so in the above example, so I'll say A can be written as A, let's say 1991, 1990, union A 1991, union A 1992, union, maybe 1990 was too early. Let's start with 2000. You can have A 2000, A 2001. Actually, you can just start with A 0, although I hope there is nobody who's 1000 years old, but mathematically there's nothing wrong with that. And you can see that this is a partition because every student belongs to one of these age groups, and no to overlap. Somebody who's born in 2000 is not born in 2001. Similarly, 2001 is different from 2002. So they are all pairwise disjoint. I need pairwise disjointness. I do need non-emptiness. So I'll have to remove the things that are non-empty. So I'll have to remove the empty years. So this is an extra step I need to do. But once I remove the empty ones, I get non-empty ones, which are pairwise disjoint, and they span they cover all of A. Every student has some age. They were born in some year. And that gives me a partition of the set of all students. I could do that because being of the same age is an equivalence relation. If I try to do this with Facebook friends, then this would not work because it's not an equivalence relation. It's not transitive. Okay. This is a very common fallacy. We try to partition sets using things that are not really equivalence relations. Yeah, so the one takeaway you need to take from this entire chapter of relations is that equivalence relations let you partition sets And actually, even the converse is true. If you have a partition, then there is a way to put an equivalence relation on the set using that partition. Okay, so equivalence relations and partitions are the same thing. So this is an example of an amazing relation in mathematics between two completely different objects. On one hand, you have relations, and on one hand, you have partitions, and they are actually secretly the same thing.